Hello and welcome to Dr. Beauty's Chemistry Essentials, A-Level Chemistry Made Easy. In this lesson we're going to be looking at measuring and calculating enthalpy changes using the equation Q equals mcΔT, which forms part of a specification point as well as one of the core practicals or PAGs that you have to do in A-Level Chemistry. In order to generate the data required to work out the enthalpy change of combustion, we need to carry out a specific type of experiment using a calorimeter. And so the setup will look something like this. And the copper container, which is a really good conductor, hence why it's used, will be full of a fixed volume of water. And the spirit burner, we would have taken a measurement of the amount of fuel in there before we start the experiment. And it's important that when we take the measurement, it is of both the spirit burner and the fuel together. And once we light the fuel, what we're going to be doing is heating up the water. So we need to take measurements both initially and later on of the temperature change. So we're going to need a thermometer. Before we move on to how the experiment plays out, the known volume of water should be between 25 to 50 centimetre cubed, in order for it to give us significant results. So we take two measurements before we start the actual heating and combustion of the fuel. We take the mass of the spirit burner plus the fuel before in grams. So take this whole thing and put it onto a balance. And then we just read off the thermometer the temperature of the water beforehand. You then burn the fuel, so it's undergoing combustion, and allow the temperature of the water to rise by approximately 20 degrees Celsius. And then you take the mass of the spirit burner plus the fuel afterwards, and then you take the final temperature reading on the thermometer. And what this is allowing us to do is to see how much of the chemical energy transferred in the fuel is converted to heat energy in warming the water. And this is labelled as Q, or energy transferred. Now, there can be some sources of error because it's not a perfect world and not all the chemical energy in the fuel gets transferred into the temperature or the heat energy of the water. So Q can sometimes be less than we expect. Firstly, if we're heating the spirit burner, that heat can dissipate out into other directions and not just heating up the water. And this is accentuated by any sort of draft that comes through here and moving the thermal energy away from the copper container and, more importantly, the water contained within it. So one method around this is to use a draft excluder, which is just a shield either side that prevents this draft from causing that issue. In this diagram, the spirit burner is quite close to the water. However, in other diagrams, there might be a big space here, and obviously, again, thermal energy is lost. So if that's the case, a suggestion that you can make is to bring the spirit burner closer to the copper container containing the water. Another issue is that when we look at what delta CH is, it's under standard temperature and pressure. However, obviously, with a hot flame, this isn't under standard conditions, so that can affect our calculation for delta CH. And on this note, the fact that the spirit burner is hot means that we actually have some of the fuel evaporating, which will affect our mass of the spirit burner fuel after and the mass of the spirit burner fuel before. So the evaporating fuel is a source of error. So this list here is just going to show you the improvements and the issues around this experiment. And number two, unfortunately, there's not really anything you can get around this. So it's just worth knowing in terms of appreciating why your data for delta CH might not be the same as the room temperature and pressure standard conditions data. So these are two solutions to the heat loss problem. However, the best solution is to use a designated device shown here called a bomb calorimeter. And so all of these conclude some of the main issues of measuring Q in order to work out combustion enthalpy in the laboratory setup. Energy transferred. So the data you can pull from this experiment includes the temperature difference between the initial temperature and the final temperature. Also the final mass of the spirit burner and the fuel minus the initial mass of the spirit burner and the fuel gives us the mass of the fuel burn. And then the final thing we had control of was the volume of the water used. Now we're going to need that in terms of the mass of the water used. And it just so happens that for 1 centimetre cubed, the density means that equals 1 gram. Now with these three sets of data, we can come up with an equation for measuring Q, the energy transferred in joules. And that is, it's the mass, which is from the mass of water, times the specific heat capacity of water, which is a constant. Now it's important to note that this will be given in the datasheet for your exam board, and it is 4.18 joules per gram per Kelvin. And we multiply this by the temperature change between the final temperature and the initial temperature of our water. Now once we've worked out Q, the energy transferred, we need to use this to work out the actual value for delta CH. And this works out to be minus Q divided by the number of moles of fuel used. There's a couple of things here. We'll come back to how we get the number of moles of fuel used from the mass of the fuel used in a moment. What you will notice is Q here is in joules. Now, delta CH, or any enthalpy, is given in a different set of units, and that is in kilojoules per mole. So, the data that generates from this first equation is in joules. Before we can input it into this equation, we need to take that joules and make it into kilojoules. So we're going to take our answer from equation 1. We're going to then, in our second step, do that Q divided by 1,000 to get it into the units of kilojoules. And then we can input that into equation 3, which will actually take us from Q to give us the enthalpy of combustion per mole. And this is why we have to take the energy transferred and divide it by the number of moles that we actually used in our experiment, because we need to know the kilojoules per mole value. So to take the mass of the fuel used and make it into the number of moles of the fuel used, we need the thing that relates this together, which is the molecular mass. And then we can take that data, as long as we can work out the molecular mass for the fuel that we're using, then we can work out the number of moles of that fuel that was used. And with this value, we place it here. Now you should appreciate that every combustion enthalpy is negative or exothermic. And so that we get a negative answer here, we put a minus in front of our equation. Let's see if you can take all those components that we spoke about in the last section and apply it to this question here. So you've been given some information, highlight exactly what that information is, and then substitute it into the correct equations to get the enthalpy of combustion, the delta CH for propan 1-ol. Pause the video now and I'll reveal the answer shortly. So if your answer works out to be minus 1,900 kilojoules per mole to 3 significant figures, then you've used the correct data and followed the correct strategy. To get there, what you needed to do was extract the information from the question correctly. So here we have the mass of the fuel. Here we have the two temperatures, the final and the initial, that are going to be used to work out that the difference is 47.3. It's worth noting here that because we're only interested in the difference between two temperature values, these units could be Kelvin or they could be degrees Celsius. It would still give you the same difference regardless of the units that are there. So this 47.3 could be in degrees Celsius or it could be in Kelvin. Doesn't matter. That can be plugged into the equation and give you the right answer. And then the final piece of data is 0.25 decimeter cubed, which we know is 250 centimeter cubed. And we know that this is, therefore, because every centimetre cubed is 1 gram. So then we need to work out the energy transferred Q. And so we're going to plug these values into the equation. Obviously the mass here, we've got two masses to use. Just always be aware that you're only using the mass of water in the Q equals mc delta T equation. 4.18 for the specific heat capacity of water. And then, having already worked out the change in temperature, is 47.3. Working this out, that gives us 49,430 joules. We then need to convert this into kilojoules so that we can take it into the delta C equation. And then, with this value, we're going to put this into the delta CH equation, which is minus Q over N, where N is the number of moles of the fuel. So to work out the number of moles of the fuel, we've been given up here, we've got 1.56 grams, and we've been given the molecular formula for propan-1-ol. So we need to take the MR of this and work out the number of moles of that, like so. And that gives us the number of moles as being 0.026. So we're going to use that in our equation, and then putting that in, remembering the minus in front because it's an exothermic reaction, will then give us the value minus 1,900 kilojoules per mole. Here we have a past paper question on using Q equals mc delta T calculations to work out delta CH. What I'd like you to do is pause the video here, read through the information on the left-hand side, and use this to answer these two questions here. A 2-marker, which is just a chemical equation, and then a 3-marker that is calculating a value for the enthalpy change of combustion of butane, delta CH. Okay, so the answers to this are going to come up now. And then what we'll do is start to look through part B, exactly the workings out in case you didn't get that right. So we have a complete combustion, so the products are going to be carbon dioxide and water. And then we just need to balance the equation to get the first mark, followed by the correct state symbols for the second mark. And it's just worth noting that butane could either be given as a gas or a liquid for this mark. So we've got the equation Q equals mc delta T, and we're going to extract the information that we need from this from the information given in the question. So we get the difference between 74 at the end, 19 at the beginning, which is 55 degrees Celsius. And whilst C is in joules per Kelvin per gram, it doesn't matter, as we've talked about before, that this is in degrees Celsius, because the difference between two values in Kelvin and the difference between two values in degrees Celsius will be the same magnitude or size. So timesing these together gives us our answer. To take that forward, we're going to turn this into kilojoules. We also then need to work out the moles of fuel that we used from the masses given. And from this mass of the fuel, we need to work out the number of moles of that fuel. And number of moles is mass over the MR. Now we know we've been using butane, so we're going to use what we worked up earlier, C4H10 as the molecular formula. So this ends up being 58 grams per mole. So we're going to take our mass, divide it by 58 to get our number of moles of the fuel. And then what remains is we're going to work out delta CH by doing minus Q, which is 11495 kilojoules, divided by the number of moles, 0.008, and then that gives us the overall answer of minus 1419 kilojoules per mole. And furthermore, part of this exam question were some questions on some of the practical elements to delta CH. So just pause the video here and see if you can answer these questions here. Okay, so I'm going to put the answers up. If there's any difficulty around this, make sure you go back and revisit the area where we looked at the practical as a whole, and where you get sources of inaccuracy and ways in which to deal with those sources of inaccuracy. So we have the loss of fuel, incomplete combustion, non-standard conditions, and even the evaporation of the water when it is undergoing a rise in temperature. And finally, ways in which you could answer the question about modifying the procedure is either using a draft shield or a bomb calorimeter. So we've looked at delta CH, combustion enthalpy, and how to measure the enthalpy changes in that situation. But we also need to be able to work out the energy change Q for a variety of different reactions. So delta RH is the enthalpy change of reactions, and within it you can also look at the very specific version of this, which is the enthalpy change of neutralisation. The delta RH, the enthalpy change of reaction, is where molar quantities of reactants react together under standard conditions with all substances in their standard states. Whereas standard enthalpy change of neutralisation is when 1 mole of hydrogen ions reacts with 1 mole of hydroxide ions to form 1 mole of water under standard conditions and standard states. An example of a reaction that is under molar quantities would be magnesium reacting with hydrochloric acid to form magnesium chloride and hydrogen gas. And obviously to balance this, we need a 2 in front of the HCl. And so this is where we're talking about molar quantities. We have 1 mole of magnesium to 2 moles of hydrochloric acid to form 1 mole of magnesium chloride to form 1 mole of hydrogen gas. Now, measuring the energy transferred for these types of reactions requires a very simple setup at A level, which is a polystyrene insulated cup. Often this is kept in a beaker, and to improve the insulation of this cup, you can put cotton wool between the polystyrene cup and the beaker. And then obviously to measure these energy transfers, we need a thermometer. And then initially you would put the reactant that is in solution in the polystyrene cup. You would take some initial measurements of the temperature of that solution. So imagine this solution is the HCl here. So you take some initial temperatures just to ensure that the solution has stabilized and equilibrated in its temperature. And then you would then add at a certain time afterwards the second reactant. Now in the case of magnesium reacting with hydrochloric acid, we would add the magnesium to here and then take the temperature some time after. In this case, we chose the aqueous solution first because we can get a temperature reading for that, and then added the solid second. But obviously, if you were looking at a neutralisation reaction, both acids and alkalis are both in aqueous solution, so you could use one or the other first. It really doesn't matter, as long as you're taking an initial temperature before addition of the second reactant. So this is a typical graph for 2 reactants reacting together. So at the very beginning, it is just reactant A from our equation that is added, and then we take readings over the next 3 minutes in order to check that the temperature has equilibrated. Then it happens that at 4 minutes, reactant B is added, and that's now when the reactants can react to form C and D. Our measurements are made at the next available time point. The reason no measurements are made at 4 minutes is because the chemist is occupied with adding reactant B to reactant A. It's clear that this is an exothermic reaction because the temperature has increased, and we can see that qualitatively. But we need to find the temperature change at the point of mixing the reactants at 4 minutes. Because on addition of reactant B, the concentrations of A and B are the highest, we have more collisions occurring, and therefore more energy released. So the heat loss at this initial part of the reaction is greatest. So we need to use an extrapolation method to actually get the true temperature change that would have happened at 4, which would be around here. Now the reason this data point is so much lower is again going back to that point that on mixing A and B are the highest concentrations, and so the heat loss is greatest. So we're going to use the extrapolation method, and we're going to create 2 lines of best fit. One for the initial temperature when it was just reactant A on its own, which will be clearly seen through these data points like so. And then a second line of best fit, which will be for when the 2 reactants are added together. You'd be tempted to draw a curved line of best fit here, but we need to remove any of the heat losses that occur. So we're going to draw a straight line of best fit. Now the second line of best fit, you might be tempted to do a curved line of best fit here, but we need to ignore any data points that will have any heat loss in them. So what we're going to do instead is choose a line of best fit between the latest data point all the way to the very initial data point that is highest. So this is higher than this data point. So we know that this has had some heat loss and this has had some heat loss, so we're going to discard these 2. This is the highest, and then we see a downward slope from there. So our line of best fit is going to be between here and here. So we extrapolate out. And then because we're interested in 4 minutes, the point of mixing, we're then going to work out the temperature change between this point here and this point here. And so already we have the y-intercept for the bottom of this delta t. And then up here we're going to have to extrapolate across in order to read the y-axis. And then we can use this information in order to input into our equation Q equals m times c times delta t, where delta t has come from this graph here. So in summary, we use the extrapolation method when doing delta RHs, whether they be just standard reactions or neutralisation reactions. And we do it because if a reaction is either highly exothermic or endothermic, then we have a lot of heat loss on mixing. So we need to extrapolate back in order to account for that heat loss that occurs. Now when calculating delta RH for a generic reaction, we use the same equation, Q equals M, where M is the mass of the water or the solution. And we assume that it is just pure water, so it will have the same specific heat capacity as water, so 4.18. And delta T is calculated using the extrapolation method we've just seen previously. So that is all fairly straightforward. The next step is working out delta RH. And this requires us to understand what N is the number of moles of. Is it the number of moles of A or is it the number of moles of B? And that all depends on which one is the limiting reagent and which one's the excess reagent. And so we need to work out the limiting reagent, the number of moles, as this will be the one that determines the molar quantities. To work out the limiting reagent, we need to work out the number of moles of A and the number of moles of B separately. Then once you've worked out the number of moles of A and B, you divide this by the molar ratio that's given in the equation. So here it'll be 1 to 1. So it'll be fairly straightforward calculation. Sometimes you need this column, sometimes you don't, but it's always worth including. And then whichever comes out as the smallest is your limiting reagent. And that will fix the number of moles in this equation here, delta RH. Now something to be aware of is this equation here. If it's endothermic, then you have a plus Q over N. As we know, endothermic transformations have a positive enthalpy change. And just like combustion, exothermic will have a delta RH with a minus in front of the Q over N in order to get the correct signage. So let's put some of these principles in action. So looking at this question here, we've been told that we have a reaction between copper sulfate and magnesium. And then we've been given some other data of the temperature rise, delta T. We've been told that we've got this amount of magnesium powder, 2 grams, and that we've got this volume and this concentration of copper sulfate. So lots going on. So we're going to have to work out which reagent is in excess and calculate the enthalpy change delta RH for the reaction. And we've been told that even though we've got copper sulfate and we're mixing magnesium to it, we should assume the density of the solution remains just like it would be in water, 1 grams per centimetre cubed, and that specific capacity is also just 4.18. It's really important to just try and have a go at this, see how far you can get. Pause the video now, do that, and then we'll reveal the step-by-step way that we approach this to get the right answer. Okay, so if you got the answer at the end as minus 525 kilojoules per mole, then you've done the correct strategy and you've used the correct data. If you haven't, we're going to go through it step by step. So first of all, let's work out what Q is, and this is no different to a combustion question. So we need M, C, and delta T. Now here we're only interested in the mass of the water or the aqueous solutions. We're going to ignore, even though we're adding 2 grams of magnesium powder to an aqueous solution, we're going to ignore this in the mass. The reason being is we're multiplying this by C, 4.18, which is the specific capacity of water or an aqueous solution. Magnesium powder itself isn't included here, so we just ignore it. So our mass of water is going to be 100 centimetre cubed or 100 grams. And then we're going to just times that by the specific heat capacity and the temperature rise of 25.1 degrees Celsius. This then gives us an answer in joules. And obviously delta H is in kilojoules, so we're just going to sort that out right now. Now we're going to work out delta RH. We already know that because we have a temperature rise, that we have an exothermic reaction. So we know we need the equation delta RH equals minus Q over N, because this minus is only used for exothermic reactions. If in this situation it was a temperature decrease, then we would change the signage for a plus, because it would be an endothermic reaction. So Q is this value here, but we need now to work out N, and remember this is the number of moles of the limiting reactant. We have 2 reactants. We have the copper sulfate, of which we're given a volume and a concentration, and we have magnesium, which we're given a mass of. So we're going to have to calculate the number of moles of the copper sulfate and the magnesium powder, and also use the molar ratios in order to work out the limiting reactant. So having constructed the balanced symbol equation, we can see that we have a 1 to 1 to 1 to 1 ratio. And so that means our reactants are 1 to 1 for when we look at dividing the number of moles over the molar ratio. Then what I've done is taken the 2 reactants from the equation, and I know magnesium I've been given a mass of 2 grams. So I know the thing that links mass and number of moles together is MR. So these are my columns here in order to get number of moles. And then my copper sulfate I've been given volume and concentration. So I put volume and concentration there because I know number of moles is volume times concentration. So now all I need to do is extract the information from the question. So I've got 100 centimetre cubed here of copper sulfate. Let's get that into decimeters cubed. So we divide by 1,000. Our concentration here is 0.2. And so we can tick these 2 pieces of information off. We've used them throughout of our equation. The reason I obviously had to divide centimetre cubed by 1,000 was to get into decimeters cubed, so it matched the units of the concentration. That then gives us the number of moles of copper sulfate as 0.2 0.02. Then I turn my attention to magnesium. I knew I had 2 grams of that, so we just put that into there. My MR is actually, in this case, an atomic mass, because it's just magnesium, and that's 24.3. So then I work out number of moles by using the equation here, mass over MR. Whilst lots of you can see we won't need this next column because it's a 1-to-1 ratio, but if this was 1-to-2 ratio, etc., it will be handy having this column here, because then it takes your number of moles and divides them by the molar ratio to give you a number that you can compare against, and the lowest number being the number that is the limiting reactant. So if we do this divided by 1, and the 1 coming from the molar ratio, and 0.02 divided by 1, then we obviously get the same result. And then you go, so the smaller number in this case is our copper sulfate at 0.02, so we can designate this as the limiting reactant. And so you use, at this point, the value up here for working out what N is. And so we're left with working out delta RH is minus 10.49 kilojoules over 0.02, which will then give us the answer of minus 525 kilojoules per mole. So here's a question for you to be able to have a go yourself. If you want no help at all, please pause the video right now and have a go. If you keep it running for a few more seconds, I will give you the balanced symbol equation so that you can work out the limiting reactant. So you can just practice the new skill. Okay, so here's the balanced symbol equation. So you've got 2 moles of nitric acid reacting every 1 mole of barium hydroxide. Pause the video now if with this balanced symbol equation you want to have a go at the actual question. Okay, so if you got the answer of minus 57.8 kilojoules per mole, then you've used the correct information and the correct strategy. If you didn't, don't worry, we're going to go through it step by step. Okay, so firstly, the mass of water is the 50 centimetre cubed of nitric acid plus the 20 centimetre cubed of the barium hydroxide solution. So altogether, we've got 70 centimetre cubed or 70 grams. Then we're going to keep this as the 4.18 joules per Kelvin per gram, specific heat capacity of water. We're going to ignore the fact that they're acids. And then our delta T is 7.9 degrees. So this gives us our Q as 2.312 kilojoules. Using the balanced symbol equation, we can construct a comparison of the 2 reactants to work out which one's the limiting reagent. As they're both solutions, it's going to be number of moles equals volume times concentration that links the data in the question to the number of moles of each reactant. And so we're just going to take that data from the question and populate our grid. And then use this to work out the number of moles of nitric acid and the number of moles of barium hydroxide. Now, to be sure which one's the limiting reagent, we do definitely need to take into account that for every 2 moles of nitric acid, it will react with 1 mole of barium hydroxide. So we need our 4th line of our grid. And we're going to do 0.05 divided by the 2 for the molar ratio here. And we've got 0.02, the moles here, divided by 1 because we've got a 2-to-1 ratio. This gives us 0.025 and 0.02. So we know that our excess reagent is the nitric acid because this is a larger value. So this is our limiting reactant at 0.02. Again, because this was temperature rise by 7.9 degrees, we need to make sure that we have a minus in front because it was an exothermic reaction. We use Q, which is 2.312, and then we divide by always whatever the limiting reactant is on this line of our grid, okay? Never this line of the grid at this stage. That is just a part of the grid that helps you decide which one's the limiting reactant. But we worked out this was the limiting reactant, so we've got 0.02. We put that in, and so this equals minus 115.6 kilojoules per mole. However, because we're dealing with a question that asks us for the enthalpy of neutralisation, and our definition for neutralisation is the formation of 1 mole of water from 1 mole of H plus ions and 1 mole of hydroxide ions. Well, if you notice, we formed 2 moles of water in this. So whilst this is the delta RH minus 115.6 kilojoules per mole, if we are to link to the actual enthalpy of neutralisation for 1 mole of this, we're going to have to take this value and divide by 2, because this value here is for the formation of 2 molecules of water. So to work out the enthalpy of neutralisation for 1 mole of water, then we're looking at minus 57.8 kilojoules per mole. So that concludes our lessons on measuring and calculating enthalpy changes using the formula Q equals mcΔT. If you found this useful, please ensure that you like the video and subscribe to the channel.